Reflective coatings and herring. Herring and related fish have a brilliant silvery appearance that camouflages them while they're swimming in a sunlit ocean. The silveriness is due to platelets attached to the surfaces of these fish. Each platelet is made up of several alternating layers of crystalline guanine, N is equal to 1.8, and of cytoplasm, N is equal to 1.333, the same as water. With a guanine layer on the outside in contact with the surrounding water, in one typical platelet, the guanine layers are 74 nanometers thick and the cytoplasm layers are 100 nanometers thick. So let's take a look at the figure here. We have alternating layers of guanine and cytoplasm in contact with the water, and the index of refraction of the water is the same as that of the cytoplasm. Part A. For the light striking the platelet surface at normal incidence, for which vacuum wavelengths of visible light will all of the reflections R1, R2, R3, R4, and R5 shown in figure be approximately in phase? So those are reflections from these interfaces. If white light is shown on this platelet, what color will be most strongly reflected? The surface of a herring has many platelets side by side with layers of different thicknesses so that all visible wavelengths are reflected. Okay, now we note that the index of refraction of the guanine layers N sub G is equal to 1.80, which is greater than that of the cytoplasm layers, which is equal to the index of refraction of water, 1.333. Okay, so let's follow the rays labeled R1 through R5. So for R1 is reflected from the water guanine interface. At this interface, I'm going from low index of refraction to high index of refraction. So there will be a phase shift. So for R1, I have, as a result of the reflection, a phase shift of pi radians. Now for R2 is the next reflection from the next interface. So that's this one. That's the reflection from guanine cytoplasm interface, going from high index to low index medium. That means there is no phase shift during this reflection. Delta phi 1 is pi, delta phi 2 is 0. And for R3, we're going to the next interface. That is R3 is here from cytoplasm to guanine. This is from low index to high index, so there will be a phase shift. Delta phi 3 will be equal to pi radians. For R4, we're going to the next interface. The next interface is here, so R4 is from guanine to cytoplasm, which is from high index to low index, so no phase shift. Delta phi 4 is equal to 0. And for R5, we have reflection from cytoplasm guanine interface, low index to high index, so there will be a phase shift. Delta phi 5 will be equal to pi radians. Okay, so we have figured out the phase shifts during these reflection processes. Okay, so let's see what is happening in guanine layers. So we have an incoming wave that gets reflected from the cytoplasm guanine interface that goes through a phase shift. And I recall that the index of refraction of the guanine layer is 1.80, and the thickness of the guanine layer is 74.0 nanometers. So because there is a phase shift of 180 degrees for this reflection, if I look at the condition for constructive interference of these two rays, I will see that the additional path difference 2Tg, delta is equal to 2Tg for close to normal incidence. In addition, I have a phase shift of pi because I'm going from low index to high index medium. So let's write the condition for constructive interference. Condition for constructive interference will be m plus 1/2 wavelength in the guanine layer equals to twice the thickness of the guanine layer. That's the path difference. Okay, now we can recall that the wavelength in the guanine layer is the wavelength in vacuum divided by the index of refraction in the guanine layer. The speed of light in the guanine layer is the speed of light in vacuum divided by the index of refraction in the guanine layer. And we know that the speed of light in the guanine layer is equal to the wavelength in the guanine layer times the frequency of light, which is determined by the source. That doesn't change depending on the medium. So writing this constructive interference condition, m plus 1/2 the wavelength in vacuum divided by the index of refraction of the guanine layer is equal to the path difference to thickness of the guanine layer. For m is equal to 0, we obtain lambda is equal to 4 index of refraction times the thickness. And if we substitute the numbers here, we're going to obtain lambda is equal to 4 times 1.8 times 74 nanometers. So we find that lambda is equal to 533 nanometers. Now, if you look at the reflection from guanine to cytoplasm interface and the light traveling inside the cytoplasm, we have the index of refraction of the cytoplasm equals to 1.333. The thickness of the cytoplasm is 100 nanometers. Now, the path difference that develops here is equal to 2Tc. So delta is equal to 2Tc. Now, when this ray gets reflected from the guanine cytoplasm interface, we go from high index to low index. There is no phase shift. But for this reflection at this interface, cytoplasm to guanine, there is a phase shift. So we will have a phase shift of pi radians for this reflection. In the previous case, we didn't have this additional phase shift because it was from high index to low index. Okay, so now we can write the condition for constructive interference. Condition for constructive interference will be m plus 1/2 lambda in the cytoplasm layer is equal to twice the thickness of the cytoplasm layer. Okay, so the lambda in the cytoplasm layer is the lambda in vacuum divided by the index of refraction of the cytoplasm layer. The speed of light in the cytoplasm layer is the speed in vacuum divided by the index of refraction of the cytoplasm layer, and that speed is equal to lambda times the frequency. Okay, so for m is equal to 0, if I look at the constructive interference condition, m equals to 0 will give me lambda divided by 2 index of refraction of the cytoplasm is equal to twice the thickness of the cytoplasm layer. So that means lambda is equal to 4 index of refraction of the cytoplasm layer multiplied by the thickness. And if I substitute the numbers here, lambda is equal to 4 times 1.333 times 100 nanometers. We find the wavelength to be, once again, 533 nanometers. Okay, so the conclusion is that the condition for constructive interference gives me lambda should be equal to 533 nanometers. Now this is green in the visible spectrum, corresponds to green light. So this will be the most strongly reflected color. All right, so that answers part A of the question. So let's remember, we were asked what color will be the most strongly reflected if white line is shown on this platelet, and normally the surface of the herring has very many platelets side by side with layers of different thicknesses so that all visible wavelengths are reflected. But for this setup that was described in the figure here, for close to normal incidence, we see that lambda is equal to 533 nanometers, which corresponds to green light is the most strongly reflected. Let's move on to part B of the problem. Explain why such a stack of layers is more reflective than a single layer of guanine with cytoplasm underneath. A stack of 5 guanine layers separated by cytoplasm layers reflects more than 80% of incident light at the wavelength for which it is tuned. So why don't we just use a single guanine cytoplasm setup here? Instead, we have this repeated pattern. Okay, so that seems to increase the amount of light that gets, intensity of the light that gets reflected. So how can we explain this? Well, we can say that since at each interface first the water, the interface with the water, then the interface between guanine and cytoplasm layers. Some more of the transmitted light so at each interface we have a reflected light and transmitted light. So we're losing some intensity to reflection and some intensity to transmission. And for the intensity that gets transmitted, this will get reflected Okay, and by increasing the number of layers, what do we achieve? That means we're increasing the number of interfaces. A higher percentage of the light gets reflected. Because at each interface we have another reflection, so part of the intensity that was lost to transmission here is recovered by this reflection, and then part that was lost to transmission here recovered by reflection, etc. So we see a more intensity for the reflected light. So that's our explanation. Let's look at part C. The color that is most strongly reflected from a platelet depends on the angle at which it is viewed. Explain why this should be so. You can see these changes in color by examining a herring from different angles. Most of the platelets on these fish are oriented in the same way so that they are vertical when the fish is swimming. Okay, so this is talking about the angle the incident light makes with respect to the normal, and the answer depends on this angle. Well, the approximation we have used for close to normal incidence, the path difference is approximately equal to twice the thickness of the layer. This approximation is valid only for close to normal incidence. Okay. And what happens if we change the angle? If the angle is changed, there will be a change in the path difference. Delta will become delta prime, which is greater than the close to normal incidence path difference 2t, so that the wavelengths that interfere constructively will also change. So that's our explanation. We have a condition for constructive interference. The path difference must be equal to m plus 1/2 lambda g. Now, if this path difference is not 2t, but something higher than that, then corresponding to m equals to 0, we're going to get a different lambda value. So this lambda value will be equal to 2 times the new path difference. Instead of 4 ngtg, it will be 2 times the new path difference, which is greater than 2tg, which means the wavelength we will get that will interfere constructively will be greater than 533 nanometers for this case. So indeed, we will see that the color will change depending on the angle with which we look at the herring, because of this change in the effective path difference between the two rays that interfere constructively.